Really? Hi. Show of hands. How many of you are already have played with VPP, FIDO, or are familiar with it? That's very few. So I'm going to have a very short introduction to FIDO before we jump into a couple of applications in the cloud native environment which is built around VPP with a bunch of other sister projects that are going on in FIDO. Okay, so let's start with. So what is FIDO? So it's a fast, scalable, and multi-platform data plane software, and it's essentially at its core it's a L2 to L4 network stack. It supports a bunch of. It can be used in a bunch of use cases, from building a vRouter, a vSwitch, gateways, firewalls, load balancing, you name it. The interesting part of VPP is, of course, the FIDO consists of a bunch of projects. VPP is at the center of it, and the key thing about VPP is that it's fast, and that's what we are going to see in the next two slides on how it is made, how it is fast. But in terms of other things, how it fits into different environments, it can support. It can run in environments like OpenStack or Kubernetes-based deployments. And it's also extensible. You saw in the previous project that they're extending it with plugins. You can use plugins to modify it to build, modify the way the packet processing happens, build your own packet processing capabilities, debugging, tracing, so on. In terms of network management, it does support configuration, stats, sampling. It makes it easy to fit into these environments. Right? And think of it as something that you can use either as a software development kit or out of the box application that you can deploy. Okay? So you saw in the first presentation by Oshiaro-san where he mentioned the comparison between VPP and the vRouter or the stack that they are building. And we saw that it breaks the 1 terabits bits per second processing barrier. And it does it on a single server with Skylake four sockets. And we should all be curious on how we achieve that. So essentially, it breaks the traditional way of packet processing from scalar packet processing to vector packet processing. It makes use of the NUMA architecture. It uses the iCache and Dcache optimization. To do that, the packet processing itself, you can think of it as built as a directed acyclic graph. So every node in the graph does a small part of packet processing. You can think of this as microservices that form the entire packet processing path. So each node, it is coded in a way that it can fit into an iCache. And through each of these nodes, instead of processing scalar packet, instead of doing scalar packet processing, we use DPDK, fetch as many in the poll mode, fetch as many packets that are there for processing as available. Something in the range of 255 will give you the max performance that we can get from VPP. So we get the whole vector of packets and pass it through the graphs based on what you want to do with the graph, V4 forwarding, V6 forwarding, SRv6, MPLS, or just L2 cross connect. Okay. Because of the vector packet processing and the way the graph organization of packet processing is done, it helps us do Dcache optimization. How do we do that? When you pass the packets in one node, let's say ether input. So DPDK gave us a bunch of packets. We saw that all of them were ether input, and they were scheduled to run in the next node that processes this packet is ether input. What happens is it makes way for prefetching the packets. So the first few packets will warm the Dcache, will warm the iCache, and then for Dcache optimization, we just keep doing prefetch. So we fetch 4 packets ahead of time while we are processing 4 packets in parallel, for example. That's called quad looping of packets. And that's what you'll see if you just go look at the code for any of the graph nodes. That's what you'll see. You'll see a quad loop or a dual loop where next 2 packets are prefetched while you are processing 2 packets. That gives you the Dcache optimization. So that was about VPP. So now coming to how it can be applied in the cloud native environments, how cloud native environment and networking there, things like the network function virtualization, or even for networking needs of application which are deployed in the cloud native environments, how this can be built, how this can be made use of. So we'll start with a few terminology and the infrastructure components that are required, and then we will jump into the use cases. We are going to touch upon IPSEC gateway and load balancer use case that is built with this infrastructure. So I think we have gone through it quite a bit since morning. So we have what is cloud native environment, anything which you can, applications that can be decomposed into microservices where each service can be packaged as its own container, and then you chain that together to form the service, is what happens in the cloud native environments. Okay, so that's what CNCF defines a microservice architecture as. So what is a cloud native network function? Again, a network function like a firewall, load balancer, whatever else, web server. If you can decompose it into smaller pieces, modular pieces, deploy them as their own containers, and network, chain them together to network to create the service. Together they create that service. That's what happens when, that is what we want to do, and we want to do that networking really fast. VPP comes in because that plays a key role in container to container networking, container to external world networking, and container to another container in a different node networking. Ligato is the piece which sort of helps you control VPP. VPP, as I mentioned, it's pure data plane. It does packet processing really well. It doesn't have too much of control plane built into it. So you need something which can coexist with VPP to give you that control, where you can programmatically control and make VPP do what you want it to do. Okay, so that's where Ligato comes in. So this applied, you can, that's just an example of how you can imagine real world network function appliances mapped to container world where they appear as virtual network functions. Okay, so here's an example. So if you want to pass traffic through a bunch of, treat the traffic in a bunch of, through a bunch of network functions, you want to do some DPI, you want to do some firewalling, then you want to do load balancing before it hits its destination. Okay, that's the logical thing that you want to do. So you want to classify the traffic, apply what network functions that packet needs to go through between say one edge to the other edge of your operation, network operation. How do you render that? How do you make it actually go onto your routers or servers and realize that is what you see below. So you need something like a network service mesh or SFC controller, which is also part of the Ligato project, which is part of the FIDO umbrella. That provides you a where you can give the logical intent of what you want to do. That derives from the logical intent. It actually deploys and helps you connect these network functions such that the packets can enter, they get classified. You have the plumbing done with VPP as the data plane, which is the V switch that you see here and here. And you deploy this network function so that the packet actually passes through the policy that you intended or the service that you wanted it to do. So what does VPP provide? It provides basic binary APIs over shared memory interface so that it can, you can pass routes to it, pass policy configurations to it, NAT44 rules to it, tunneling configurations to it via these APIs. And also fetch, similarly you can fetch stats and stuff through that shared memory interface. But that's like really low level. You need to understand that APIs, break down your intent into those APIs to achieve anything. So what did we do? Of course, there are other projects like Honeycomb, which is also part of FIDO, which gives netconf, resconf phase interface. So there was Java bindings built over this C low-level APIs, which would give you a young way of talking to VPP. But that's not really useful in the cloud-native environment. Like Kubernetes, you need everything is built around the CNI infrastructure, which is Go-based, and the way you want to communicate with these plugins is mostly based on protobuf serialized messages over gRPC-like interface. So that's what we built with Ligato VPP Agent. So this becomes part of the infrastructure to talk to VPP. So it is co-located with VPP. It sits. It's co-located with VPP. It provides. It uses the Go VPP language bindings built on top of the binary VPP APIs, and it gives northbound to any of this CNI interface. It will give a protobuf based API over multiple transports. gRPC is one of them. Okay. Excuse me. Of course, it needs to be compact. It should not be very heavy. This whole Ligato VPP agent is a single binary which can be deployed as another container. If VPP is deployed as a Docker container, it can sit next to it in the same pod where you can use gRPC messages to pass to this Ligato VPP agent, which in turn goes and talks southbound VPP binary APIs using the Go bindings, and configures VPP and makes VPP do what it wants, what you want it to do. So in summary, so these are the infrastructure components. So VPP is the data plane plus gives a binary APIs to talk to it. Go VPP is a language binding, Go language binding. VPP also supports Python, Java, C++, all the other language bindings to talk to it. But for this purpose, for the CNI purpose, we use Go VPP bindings. And then there is VPP agent, which we just saw, which is very modular, lightweight, and gives northbound high-level protobuf based gRPC interface, and configures VPP the way you want it. So I mentioned that VPP is a flexible, extensible architecture. So you can, it provides v4 forwarding, v6 lookup, all this as part of the core VPP, but you can always add plugins which are runtime drops, load time drops, where you can build a shared library plugin which can, once dropped into the plugin directory, you restart VPP, it will, you can change the graph, it dynamically changes the graph of packet processing. So you can add like the GTPU example that you provide, he provided, or the new COS, 5G COS thing for UPF that was being built. All this will be built as shared libraries which will sit on the, which when dropped into VPP will change the way it processes packets. Okay. So each of such plugins can also give how you configure them. If you want that 5G COS to be enabled, it would give its own APIs on how to enable it, for what packets, for what deployments to use that APIs. So to fit into the same flexible architecture, the VPP agent, the Ligato VPP agent is also built in this pluggable fashion. So here's an example. So what you see here is a bunch of plugins. It's again plugin architecture. So if you want to configure ACL, L2, L3 features, or NAT44, any of these other things, so all this can be plugged into this VPP agent. It will talk, it will give a modeled interface northbound to configure any of these features, and southbound it will talk binary APIs to VPP to go and configure the respective plugins as the requests are received. And you can receive requests from various protocols, either a key value pair etcd that we saw in MJ's presentation, or it could come, you can hook in any kind of message bus to pass this protobuf message to this VPP agent, which will then go and configure VPP. So this can be anything, and we will go into the example use case with Contiv, which builds another layer of how it integrates into the Kubernetes ecosystem. Okay. So we saw the infrastructure pieces which go with VPP. Now, how we make it interwork with the Kubernetes ecosystem is what we see here. So the Contiv CNI has a bunch of plugins, or rather containers that go with it, so that you can, I think the picture will be better. So here it is. So again we go back to MJ's earlier presentation. So you have the master node, you have minions. So to make this whole network So typically the CNI is good for application networking, right? So you give application policies, you label the nodes, and it maps it and goes and configures the Linux networking stack with IP tables and filtering rules, and creates the virtual interfaces or tap interfaces that are needed for the container application container networking. But you may want a little more than that for network function virtualization, because that's not a typical application. That you really need high performing packet processing done by these applications. So what we have done is modified this. It still implements the CNI Kubernetes CNI APIs, but this is how it does it. So on the master node you have it will build its own etcd, which is a key value store for the configuration. It runs a state reflector, and on the minions, on the worker Kubernetes nodes, we have the actual Contiv CNI plugin which will listen to these messages. It uses the Ligato VPP agent that we saw as a library, and drives the policies and services that needs networking related changes or networking related plumbing into the VPP via this interface. Okay. And this other piece is called steal the network interface. So typically you would expect that there is a management interface to get any of the master to minion communication, while the data interface will be going through this DPDK set of ports. But if you don't really have it, and if you want to really combine it, then you may want to introduce this plugin to just steal the NIC from VPP, because once it runs DPDK, it owns the NICs completely. So you want to pass the packets through this CNI interface, you would do this. We have introduced this piece, and this etcd is different from the Kubernetes etcd. So this purely maintains the Contiv VPP or network related configuration in the key value pair. Okay. So this is how it will be stitched. External. Okay. So once you have your services defined and they are plumbed with VPP as the vSwitch plugin, this is what happens. So there are two. So there are two nodes here. So we have a bunch of pods which run services. This is the VPP vSwitch running on each of the pods, and external communication is stitched together using typically VXLAN. You could use other tunneling mechanisms as well. But internally it would per pod it can give tap interfaces when you don't have high packet processing or high packet transfer requirements. But we do have something else called a MEM interface, which you can think of as an equivalent to the vhost virtuio vhost interface that is provided for VMs. So VPP has built something similar, which is a shared memory based interface with a separate Unix domain socket for control plane. So that could plug in your pods to this switch. So any packet coming in, you render the service based on how it is chained together through these pods, and VPP takes care of sending the packet through it, getting it back, sending it to different pods, and then if the service spans across nodes, it would again be stitched through a VXLAN interface here, and you will achieve whatever you wanted to do. So this is this again sort of gives the bigger the complete picture of how you can deploy servers as nodes, deploy different pods to do different services, and use DPDK with VPP to stitch multiple nodes together, and within the node use VPP to stitch the services together. One other interesting thing is the pod could be something like an Nginx server that's just running inside the pod. You have a web service hosted inside a pod, and you expect VPP to plumb and give the packets that are coming for that web server into it. In that case, you don't really need to run VPP inside the pod. But you may want something like the MEM interface that I mentioned, where you have a IPSEC gateway, for example, running inside a pod. That is your service. Then you would want VPP to be co-located there, because that would give you the additional benefit of some of the IPSEC functions that are already built into VPP that could be made use of, or some packet processing. Your network function, virtualized network function itself could be built using VPP as the function. Okay, so you can modify the packet processing and make whatever you wanted to do with your network function in VPP, and that becomes its own pod. Or you could run, it also supports a host stack where you can run you can build your TCP UDP based applications, TCP applications for now, and make it consume packets from VPP as instead of using the native Linux network stack. In interest of time, I'm going to just skip this, give you this example of load balancing. This is how it is, we are defining a load balancing service in Kubernetes terms. So you see there is 3 replicas of Nginx application being deployed as a service, and we want a load balancer. So for external load balancing we are using Metal LB, so there is you can refer to that, this when deployed results in a load balancer with 3 pods running Nginx web services. So they expose an external IP address, then we have a proxy ARP to for this address, and then the packets are load balanced using NAT44 and ACLs by VPP. So this gives you an example of VPP configuration. So it has trap interfaces to I think this will. So this is how you can load balance. There are 2 ways, of course. This is the proxy ARP based one with HA kind of configuration here, while this is mostly a BGP based policy where the external load balancer will route the packets between the VPPs, and this was what you saw in the VPP configuration. So there are 2 pods running Nginx there, so you will have tap interfaces to connect to the Nginx pods. This is the NAT44 configuration, so that you can do load balancing with the specified probability, load sharing. And of course this VPP node here should do proxy ARP for the IP address, so that you can get the packets. So that was about the load balancing service built as part of the in the Kubernetes ecosystem. Instead of using the kube-proxy's load balancing, you could as well use this kind of replaces. This load balancer will replace kube-proxy. You don't have to run kube-proxy if this is running, and that will give you. You are bypassing the Linux networking stack. You can use DPDK plus VPP to get the near bare metal speeds that you want for packet processing. This is another example of VPP application. So it is, we are taking the example of IPSEC gateway. So what VPP natively supports uses DPDK crypto and supports IPSEC with a IQ2 built into it. But that is not very useful when you want to deploy it as IPSEC gateway service in the Kubernetes environment. So what we have, this is the vision. So how about doing it with something that is out there, which is mostly used for IPSEC gateway? StrongSwan is one such example for deploying it. So if you see this, this is how it is typically deployed today without VPP, without this whole environment. So it uses Linux environment, and you can't really get the line rate or high speed performance for packet processing for IPSEC encryption, decryption. So what we want to do is use StrongSwan control plane as a control plane, and VPP with DPDK IPSEC data plane to get high performance. And then you can imagine that this can then be wrapped into this whole Ligato Contiv CNI infrastructure to deploy this IPSEC gateway as VPN gateways or services in the Kubernetes environment. So I'm kind of out of time, so I'll probably wrap up. This gives the bigger picture of how this additional component, which is the StrongSwan APIs that where you can specify the intent, which will drive it back into this agent, which then talks to the Ligato VPP agent and then configures VPP to do IPSEC. And the whole SA formation, the IKE stuff, key and authent will happen here, while the actual encryption and adding the ESP-AH header, decoding or encoding, the encrypting or decrypting will happen in the VPP with help of DPDK. And here you see we need high performance MEM interfaces, which are like the vhost interfaces, instead of tap interfaces between the pods. That's all I had. We saw some of the infrastructure components which you can build your own network function virtualization from. You can build and deploy using the Ligato VPP Agent, Contiv VPP plus VPP as the data plane. Here are some references if you want to get started. There is a Vagrant setup which is pretty quick. You can bring up that whole load balancing setup with just doing a Vagrant up and getting this whole environment set up for you to play with. To get started with VPP or any of the other FIDO code, you can refer to these links. These are all part of the schedule. It's published there, so you should be able to use it.
Thanks, Shwetha. 2-3 questions for Shwetha. Any?
Yeah, do you have any performance numbers? What we would get as a gain using VPP?
Yeah. So there is a CI/CD environment, and there is a project called CSIT, which is part of IDO. I'll probably update this slide with the link to that, where we have the trending performance continuously measured as we add features into VPP. So if with Skylake, for example, for IPv4 forwarding, we are getting something like 23 million packets per second per core, and we get line rate if 40 Gbps port is what is attached. With one core, we are able to get line rate forwarding performance. With V6, we can process a few lesser million packets per second in the range of 10 million packets per second. But the current trend, and you can monitor, there is a dashboard which continuously measures IPSEC, VPP as MEM interface performance numbers, V4, V6 forwarding. All this is published as a trend in the dashboard. I'll update the slide with that link.
Hi, Shwetha. Thank you for that info. Here. Thank you for the info. Can we go to slide 18? I have a query there. Yeah. Okay, it's okay. In slide 18, you mentioned the pod can run VPP, and with the example of IPSEC in place. I just would like to know, is that VPP MEMF interface is extended just like Vertio crypto, where the pod and the host VPP talk with each other and say that I have a capability for crypto on the host to be offloaded, and rather than doing it in the soft crypto on the pod, directly send it down and get it done? Do we have that?
I doubt if that is there, but I would go back and check again. But the MEM interface that uses just talks between the VPP as the VPP vSwitch and the pod VPP.
Yes,
the pod VPP, I don't think. So this whole node discovery capability, so that you can actually offload and use, when not using DPDK, still use the capabilities of the device, is not there yet.
Yeah, still it's a long question actually. Okay, one question she can take. Yeah.
So you mentioned that you use a MEM interface to communicate between control plane and the VPP data plane, right?
Can, yeah.
So there are applications where you have a lot of control plane messages.
Correct.
So have you studied or did you study the performance impact where you have a lot of control plane messages, and then how does the VPP data plane performance vary in those conditions?
The performance of MEM interface itself is well known. It can, with again Skylake with turbo mode, you can get like 5 million packets per second that it can process with V4 routing. VPP, it can be tuned. So typically when you deploy VPP in multiple cores. Some of them are running as core worker threads, while there is a main thread running which does all this control plane API handling, that where you get the request for updating your fib or updating your the way you are processing the packet. I am sure there is some tests which cover that and dump the performance numbers for that. I need to go back and look up. But if you go to CSIT project in FIDO, there is a whole the test that we run and the performance, the current performance with the is published. If it is not covered, I think just reach out to us. I think that's something which we can do.
Sure. Thank you.
Thank you, Shwetha. Thank you.